Hey guys, what's up? Eddie Aho here with KissAnalog.com. Hey, today I am going to measure my resistor. I'm going to find out how inductive or non-inductive this resistor really is. So it's supposed to be a non-inductive resistor. I use it for audio testing. This is the 4 ohm and here's the 8 ohm. So I'm going to do the 8 ohm. We might have time to do the 4 ohm as well. So hey, I'm going to use this GW Instack, which has a really cool way of doing it automatically, and now manually you can do it as well. Let me explain how it's done. You dial up a frequency, you inject that frequency voltage into your resistor, you measure the current, and with the voltage probe, you measure the voltage. You take the voltage, let the scope do it for you, take the voltage divided by the current, and you get ohms, impedance, right? So now resistor has no phase angle. The resistor is just so many ohms. An inductor has a plus 90-degree phase angle. It's inductive, and capacitive is going to have a negative 90-degree phase angle. So the impedance of an inductor is, or capacitors, are X's, and it's X of L instead of R. It's for resistor. It's X of L is equal to 2 pi FL. X of C is 1 over 2 pi FC. And so you can come up with those things. You take, if you have some inductance, capacitance, and resistance in your impedance measurement, that's why we call it impedance, because it's not just resistance or it's not just reactance. It's everything combined. It's impedance, and we call that Z. So Z equals so many ohms, and we can measure it here. So besides this ohms measurement, we'll also get a phase angle, okay? And that's what is really cool here. I'm going to show you how that's done, and in future videos we're going to do a speaker impedance. And a capacitor, an inductor, resistor, they all have what we call parasitics. They're the imperfections, if you want. You know, for instance, resistor, right? Non-inductive, but then you have these long leads, so they're going to create some inductance. Just the fact that you have some lead length. A through-hole part, even a surface mount part, they have lead length. So imagine this is a gigantic surface mount. Well, imagine we're zoomed in on a small surface mount part, and we have these little pads here. Just the length of those pads adds some inductance. So at some frequencies, the higher the frequency is, the more the parasitics come into play. For audio stuff, 20 hertz to 20 kilohertz, it's surprising, but you still get parasitics even at those frequencies. So that's why we call these non-inductive resistors. I'm going to grab a resistor, another resistor. I want to show you the difference between two types of resistors. Alright, had to grab it. This is something I bought off Amazon. I bought a lot of stuff off Amazon. This one's 300 watts. This is 200 watts. Okay, now I'm just going to pull this out of the package. I think there's some metal legs on here that I can put on this thing, but here, let's just pull this out, because this will be easier to demonstrate or to explain what I want to do. I'm going to see if I can zoom in on this in a moment. I'll bring the camera up close, but you can see from these pins here that there's this kind of a flat piece of copper wound across here. Now what's interesting is it looks like a basket weave, then all of a sudden it goes back the other way. Alright, so that is the way that resistor is wound. You see, it's kind of turns out to be kind of a weave. And the reason they do that is to make a resistor, they take a certain kind of wire and they wrap it around, and you have so much resistance. Well, when they do that, they just made a coil, right? That's pretty obvious when it's this shape. But even if it's square, you know, if you have current going into a loop, whether it's square or round, you're going to get inductance. And so to make a non-inductive, they take the same amount of turns back the other direction. Now, they have to actually wrap them. So if you go clockwise one way and the current's going clockwise, when it comes back, it has to go counterclockwise. So those two fields equalize and cancel. Now you might understand why when we take leads, like you might see on my bench, these twisted wires, essentially that's what that's doing. when you take a twist like this, every time those wires cross each other, they're essentially canceling the inductive field between twists. Okay, that's what you're attempting to do when you twist wires. Okay, and that's what you do on these resistors. So I think we'll measure these two resistors, and I was just looking at the ohms. Actually, this is a 4 ohm. So you know what? We'll measure all three resistors. So that way we can compare 4 to 4. But I want to measure the 8 ohms too. Now, if there is some inductance, the 8 ohms, because it has more ohms, might have a little bit more inductance than the 4 ohms. So we'll look for that when we do the test. All right, let's come over here and do it. All right, so for the scope setup, I've got my voltage probe in channel 1. That's the scope probe times 1 times 10. It's in the 10x position on the probe. Over here I have the Handtech CC65 current clamp, and it's also in the times 10 position on the current clamp. So I want to make sure my scope's set up that way. Well, then I'm only using these 2 channels, but I have a bunch of things all set up for this kind of measurement. So what I've done, because you know sometimes it takes a while to go set up everything, I've gotten this save menu and I've saved my setup. So now I can go recall setup, and I'll show you it's in position 5, set 5, and I can just say recall now. So it recalls it. So that really saves me a lot of time. Now just to show you real quick, channel 1, it's an AC coupling, 1 meg. I have AC coupling because we're looking at AC signals, so it just simplifies things. I don't expect there to be a DC offset, but hey, I just put it there. And then impedance 1 meg, inverts off, full bandwidth, and probe settings 10x. Channel 2, same way. Normally I would put this channel 2 on current, but it's on voltage because we're just going to do division between these 2 channels, and it's a gain setting, so it's not really going to care. So I didn't worry about that, okay? Alright, so for the cool part about this scope, we can do this measurement kind of automatically. It has 2 generators in back here. One of them we're going to use for the setup. So we come out of the generator with these little clip-ons. It'll clip onto our devices we're going to test. Okay, and then the scope's going to sweep that generator and take readings off these 2 channels and do some division, give us a gain and phase plot. Alright, so how it's going to do that, we have to go to this app menu. And then it comes with the app right here. It's just like your phone, you have applications. So now you got this app window. Let me zoom in on the app window so you can see closer. Alright, so then we come up with all these different apps, okay? And the one we care about is this FR8, the Frequency Response Analyzer. So I select that, and then I select it here, and then it says, do you really want it? And I said, yes, I really do. So then it goes to the app. There we are. Alright, so then in this thing, I've also got the setup saved. You know, this whole entire setup was saved, how I showed you before, but I'll just show you how what was set up. The input source, I put channel 2. That's the current, right? Because the way the gain is it's output over input. So the output is here, channel 1, that's the voltage. So voltage divided by current. Output over input is gain. Now the generator, that's what this is. The arbitrary wave gen. So it's set for 20 hertz to 20 kilohertz, and 2 volts was the max, okay? And it's set for low impedance. It's got low and high. Low is 50 ohms, so that's how we got that all set up. And then points per decade. You start off with a minimum of 10, you can go 15, 30, up to 90, and you just get better resolution. But just so the video goes a little faster, I'll just select 15, what the heck. Okay, so now what we do is, there's a reference circuit you can look at. You know, it kind of tells you how to set up, but, okay, so we've got the setup menu, and then there's an analyze. Once we've scanned something, we can go to this analyze window, okay? I'll zoom in to this window, and we'll start taking our measurements. Alright, so now that we're zoomed in, I'm going to turn off these menus here. Hit that guy, hit it again. And now what I've got is, you can see the scale here. It's 10 hertz to 100K. And this is the kind of play button. That's kind of the run button. And this one here's the measurement button. so we can measure it later. And over here, it's going to tell us the frequency as it starts to scan down here. And the gain and phase will show up here as it moves along, as it plots. And the phase is over here. And right now it starts off at -180 to +180. And over here the gain is, what is the gain? The gain is 62 here, 92 here. It's like 5 dBs per division. So it actually started to scan, and I paused it. So before you start to scan, it has more grids across here, and it auto scales. So I just kind of started auto scale it, but maybe I should have left it for you. But anyway, so that's kind of the way it starts up. Now, if you remember, we didn't set up the trigger or horizontal scale buttons on the scope because I had all that saved, but it doesn't really apply to this measurement because it takes care of that automatically. Okay, so I'm going to hit this button right below this. You can't see the buttons, I'm zoomed in so close, but see this little run button right here in the left corner? You can see my finger right below it. I'm going to hit the button and we're going to start scanning. Okay, here goes. Now this is a 20 ohm resistor, our reference resistor. This is our calibration shot. So here we go. Alright, so you can see it's right along 26 dB. See that gain? It's I hope the blue's coming through. The blue gain right here is this trace, and the red one is kind of angling up, and that's the red phase here. Alright, so it finished, and that is the 27 dB line is that scale line right there, and it started right about 27, but then it dipped down below. 26 dB is about 20 ohms. So you just take this dB scale, divide by 20, and then take the anti-log, and you'll get your ohms. Okay, so we're taking the voltage reading and dividing by the current reading, which gives us the ohms. And now the interesting thing is it's flat like you'd expect it. It's got a little bit of a curve up here at the end. There's probably a little bit of inductance maybe that's starting to happen. But this red one, the phase, we would have expected that to be flat too because it's a resistor, right? Or maybe turn up here with this where it's turning here. Well, I think this is what we're also doing is we're kind of calibrating the current probe, our setup. And the voltage probe I'm sure is flat, but the current probe I think has, it's dipping here and kind of climbing here. So let's turn on this button here, right below, see where my finger is here, right below here is measurement thing. I'm going to hit that button and we come up with these. Okay, so I can go to scale and it shows my scale things here, or this FR8 utility where I can save things. But what I want to do is I want to come over here to measurement. So I hit the button underneath that one, and then I have my cursor and I can set gain or phase. But the kind of cool thing about this is here, I'll show you. Turn on the cursor, then it says select 1 or 2. So I'll just select 1 right now, and 1 is set up right here. You can see that number 1 moving. I'm going to leave it over here on back to the side. I'm going to take number 2 and move it over to the far side. But see how flat that gain is, how it's crossing? But now here's the cool thing about it, is whether I select gain or phase, I get gain here and phase here, where my cursors are. So you can see the gains are pretty flat, and then the phase right here is changing a little bit. So right through here, the phase is pretty close to 0. So you know, between I don't know, let's say between 100 hertz and 1K or 2K, it's fair. It's not changed a lot. You know, right here the gain is -4.4, and right here it's +3, so it's plus minus 3 or 4 degrees through here. So right here is about 4, so it's fairly flat, I would say, between the center range from 100 hertz to past 1K to maybe 2 or 3 kilohertz. Then it comes up and we'll go to 20K right there at the end. So what we have is 26.77 dB here, and we have 28.19 dB over here. And this phase is started off -17, so a negative phase is going to be indicative of, like a capacitive. So it looks kind of capacitive. And then over here it's 33 at this end. So we have a total of 50 degree shift from here to here, and 1.42 dB. That's not too bad for the gain. That's pretty flat. So that's a pretty good reference. Alright, let me just turn off these menus so we can see a little bit more display. There we go. So this is our reference display. We can kind of count on our test setup being pretty good for gain, pretty flat, and maybe just a slight curl up if we just remember that we got to basically take our other measurements and subtract whatever changes here. So here where we're seeing it climb up 33 degrees, we got to remember that if we see another measurement where we have a 33 degree climb, that's most likely the current probe here. And -17, so it looks like it starts turning into a little bit of an inductor, which is not too surprising on a current probe, because kind of some inductive pickup there. And then it looks a little more capacitive down here. It could be the filtering in the current probe. Alright, so next up is my 8 ohm 200 watt load. Let's see how well that is going to behave. I just hit my app button and this stuff comes back up, so I'm going to go to FR8 measure. Actually, I need to go back to take on a new run. Okay, here we go. Okay, gain starting off very flat. So the log of 8 ohms times 20 is 18. So it looks like there's 18, it looks like we're just above, and then it drops down to 18. So it looks like it's coming in pretty good. Okay, and there we go. Now again, what we saw before, we started off with our reference at about -18, right? Here, let's turn up these cursors so we can get our cursors over there. Okay, there's channel 2. Okay, they're already kind of set up. So here, let's turn off these so we can measure them. So you can see the gain started off at 17, almost exactly what the current probe did. Yeah, it's almost dead on. So it looks like my 8 ohm resistor is very resistive up to about here. And then let's see, this finished at 49.9. And our reference was 31.6, so it's only gone up about 18 degrees. So it should have, on the graph, it should have gone up to about 18, which would have been about where this blue line is. So it should have came up right about there. So it would have looked kind of like this, just a little small turn. So probably after about 2 kilohertz. Here, let's turn. So let's see where we are. Right here, our phase is about 1 degree, and we're about 7 degrees there. Let's say at 10K we're about 27, and if we subtract that from the other thing, we're probably only a few degrees up. So I would say it's pretty flat from all the way up to 10K, my resistor. So, and even at 20K, it's only going up an extra 17 degrees, so that's not too bad. So I guess I feel pretty good about my load resistor. Alright, you know, I put the big green 4 ohm on, so let's do the 4 ohms back to back. Alright, let's do it. Alright, get that menu and then hit FR run. Here we go. Now, you know, I thought I just did the 4 ohm silver, but I did the 8 ohm silver, so then I was going to do the 2 4 ohms. So that's okay. I went 8 ohm silver, now 4 ohm green. Now we're going to go back to the 4 ohm silver after this. But let's measure this. Okay, it does look very flat, doesn't it? And started off 12.92 and went to 13.75, so that's less than dB. That's pretty darn flat. The degree started off at 18 minus 18.19. Again, very similar to our reference. So I think we're not really. I think we're really starting off pretty flat here. And it ended at 37, which our reference was 31. So again, I think it's only about 6 degrees going up here at the end. So I think this green resistor looks very non-inductive. Let's do the silver 4 ohm. Okay, so let's hit the app button and go back, and let's do the run measurement on the other 4 ohm, the silver. Okay, so let's see. Just get the cursor so we can measure that faster. 12.74. Well, you know, it is what it is, I guess. These numbers look very similar. So it changed about 2.3 dB. That's a little bit more change than the 8 ohm did. Okay, and the degrees changed about 76. But this minus 17 is about what our reference is. And the 58.53 is, our reference is 31, so it's about 27 degrees. So 27 degrees is right around in here, so it should have only gone up to about here. Not too bad. Alright, so let's do the speaker, and I'm going to increase this points per decade because I don't think we're going to need to go to 90. Let's go to 45 instead of, we were doing 15, but I think we ought to go to 45 points per decade because I suspect the speaker response is going to have a little bit more interesting curves in it. So let's get a little bit more detail. Alright, so here we go, FR run. And we'll be able to hear it, so I'll keep quiet. Okay, I think I woke up my dogs with that one. Geez. Okay, so the gain, look at this thing all over the place. Now actually through here it's not too bad, but wow, look at the rest of this stuff. Let's get the cursors up. Okay, let's get the cursors turned on. And okay, so 2 is sitting out here. You know what? Let's just see what it did. Down here on this low point, it looks like at 19.6, 25 up here, and let's see how high that peak is. Goes up to 30, and drops down to 15.2. That looks like 25.2, and then right through here, it's about 17, 15.6. You know, it's right through here is fairly flat. That's 19.47 right there. So you know what? Let me put this at the low one. I think let's put this right here, and then let's get cursor 1 and go to the high point, that peak. Those are kind of the worst case. Yeah. Okay, so it was up to high as 30.8 it looks like, and as low as 15.2. 20, but okay, look at this phase. If you look at the gain here, it's as the frequency goes up, it's dropping. So that is indicative of a capacitive nature. You know, like, and then it kind of flattens out. That's kind of resistive, and then it goes up, and that's inductive. But where capacitive and inductive meet is a resonance, but it's really flat, so it's like it's really dampened with the resistance of the speaker wire, probably, or crossover, I'm not sure. And then it comes up pretty sharp, and then it drops sharp. So that's pretty sharp resonance right there. That happened at 70 hertz. And then it drops, and kind of like this, it's dampened by resistance before it goes inductive again. And that happened at about 160 hertz. Then out here around, let's see, 2, 3, 4, 5, around 600 hertz, it had another resonance. So there's like 1, 2, 3, 4 resonant points, and then another one here. Now you notice how it kind of looked a little jaggedy. It looked like, I think there's a pole here, you know, a pole here and a zero here. It's like it's moving up and then down, and then it kind of wiggles like that. So I think there's some pretty complicated filtering going on right through here. I think, from my guess, is they were trying to make it flat through this section. As a center speaker, they're probably more interested in these frequencies for the center, I'm guessing. I don't know. Or maybe they're bumping it up through here, a little amplification through there. Yeah, this speaker definitely has some characteristics to it, and it's noted as a 8-ohm typical speaker. All right, guys, that was pretty interesting, right? Here's the big old green guy. Put the little shaft thing through here with the little ceramic insulators on the end, and the little feet stand up. So that's kind of nice, because then you don't have to worry about putting on wood and shorting things out and burning wood. You can put it down on metal or anything you want. But anyway, that's what it looks like, and it's actually a little bit less inductive than this guy. But I think they both performed very well. So yeah, hope you liked that video, and hope that helped you, learn something about inductance and resistors and how you can use your scope to capture that. We're going to be doing some more impedance measurements with other components, capacitors and inductors and such. So next one's going to be speaker. Let's do that next. Alright, hey, thanks for watching, guys. Thumbs up if you liked it. Okay, see you next time.